You're welcome to this class once again. I'm your physics instructor. Today we will be looking at a topic that is very, very interesting in physics. That is wave motion. When you talk about wave, it's a common word. Wave of that, wave of this. But in physical deduction, wave is a different thing entirely. Let's consider wave in this form. Sometimes, when you throw something inside a water bath, for example, that thing you throw inside a water bath, you observe that it creates a disturbance to the water. As it creates a disturbance, let's assume this is the water when it is in its calm state. By the time you drop that stuff inside the water, something will happen. It will create something that looks like this, where the impact of that thing goes beneath. So it drops down, it will create something like this. So the direction at which that body hits the water, the direction is at this direction. But there is something that travels in this direction. The thing that travels in this direction is wave. So there is a displacement, but the direction at which that thing goes is not the direction at which the wave itself is going. So the wave travels, but it does not cause a permanent displacement of the medium molecules itself. The water, we're talking about water, which is the medium. When you throw that body inside the water, you see it enters, it moves. As it's moving, it is the wave that is causing that upward and downward movement. But the actual molecules of the medium itself is not moving. It's just vibrating about what we call a to and fro motion. We talked about that in vibrational motion or oscillatory motion. So it's just a to and fro movement. It goes down, it comes up, it goes down. But you watching the water, you see that the water is moving. That thing that is causing that movement, that energy that you see moving, that energy as it's moving inside the water, that energy is what we call wave. And the motion at which it moves is what we call wave motion. So the energy that you see moving, causing that molecules to vibrate in that to and fro motion, is the wave. The motion they cause is wave motion. So we can define wave directly as wave is defined as a disturbance which travels through a medium. A medium, example of a medium is water, or a string, or a rope. Wave is a disturbance which travels through a medium, transferring energy from one point to another within the medium, but without causing a permanent displacement of the medium itself. So we say, the first thing you must take about definition of a wave. One, you write this down. One, it does not cause a permanent displacement of the medium molecules itself, number one. Two, it transfers energy from one point to another. So know that wave itself is a disturbance which transfers energy from one point to another within a medium, but without causing a permanent displacement of the medium molecules itself. So it's a disturbance. It transfers energy from one point to another, but it does not cause a permanent displacement of the medium molecule itself. Three things. The fourth thing you must take note about wave is that energy that moves, that causes that up and down movement, itself is wave. But the motion that it causes is called the wave motion. So now, from there, that will move us to the next stage by asking ourselves, wave, 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 wave. This wave, how many classes of wave do we have? We have just 2 classes of wave. So we can call it classes of wave. So that's classes of wave that we're talking about. The first one is simple. It's called mechanical wave. Mechanical wave. That's the first one. The second one is what they call electromagnetic wave. So the 2 classes of waves is mechanical wave and electromagnetic wave. Now you ask me this question: what is the difference between mechanical wave and electromagnetic wave? Why is this mechanical? Why is this electromagnetic wave? It's simple. A mechanical wave is that wave that needs a material medium for its propagation. If you want to propagate a mechanical wave, any wave that you propagate that has to do with a material medium, that wave is called a mechanical wave. Material medium is needed. A material medium is needed for mechanical wave to be achieved. But for an electromagnetic wave, no material medium is needed. Example of a mechanical wave is water wave. You need sound wave. Those are mechanical wave. Sound wave. The wave of a plucked string. Maybe a guitar string, you pluck it. Those are mechanical waves because they need material medium. They need molecular material medium for their propagation. But for electromagnetic wave, no. It passes through an empty space. It's propagated through an empty space. It is from the electromagnetic wave. That's where the present day bomb structure they call the EMP was created from. EMP. Because I've heard of the EMP. Electromagnetic pulse. It's a kind of bomb that is being created. It can fuse out the whole electricity in a city in a twinkle of an eye. So, because it travels through an empty space. So you call the electromagnetic wave. It does not need material medium. One example of one of them that you should know is, okay, for example, this one, mechanical we have water wave, and we have a wave in a plucked string, and another one we can talk about is sound. Is the sound wave. So these are examples of mechanical wave that need material medium. Another, for electromagnetic wave, they don't need material medium. One of example of that one is the X-ray. The X-ray, you have we have the gamma ray. These are examples of electromagnetic wave that don't need any material medium for propagation. So remember this, there are 2 classes of wave. The first one is the mechanical wave and the second is the electromagnetic wave. Now, that is that. Okay, we've talked about the classes of wave. After talking about classes of wave, let's see these classes of wave as an example. Let's not talk about what we call types of wave itself. Let's see types of wave. And after types of wave, we'll now move on to what we call the wavefront. Now, types of wave. Now, the types of wave that we have is simple. Basically, waves are of 2 types. The first type of wave, you must remember, types of wave. The first type of wave we must remember is that wave is called transverse wave. It's called transverse wave. The second one is longitudinal wave. So you have two types of wave: the transverse wave and the longitudinal wave. So you have the transverse wave, longitudinal wave. So two types of wave: transverse wave, longitudinal wave. Now I'm going to differentiate what makes this wave called a transverse wave and why this one is called a longitudinal wave. Now, a transverse wave is a wave that the direction of vibration is always different. That's vibration, the direction of vibration of the body causing the wave is always different. Or sorry, it's always perpendicular to the direction of the travel of the wave. If the wave is traveling this direction, the vibration will be traveling this direction. So if this is the direction of wave, then this will be the direction of vibration. So the vibration is always perpendicular. That's the word, the perpendicular. You see this, remember this 90-degree sign? So whenever you see that 90-degree sign, it means it is perpendicular. So the direction of the wave, the direction of vibration, that is what it is. So direction of wave, direction of vibration. So this kind of wave is said to be a longitudinal wave because the direction of the wave is always different from the direction of the vibration. So in the water wave that we discussed, if you throw a stone inside the water, it goes down. This is the direction of the vibration. As the body is vibrating down, the wave is moving like this. So the direction of vibration is like the while the direction of wave. So that makes it to be perpendicular. So you will not tell yourself, what is transverse wave? You see, transverse wave is a kind of wave where the direction of vibration of the wave is always perpendicular to the direction of travel of the wave. So if the wave and the direction of the wave travel is perpendicular to the direction of the vibration, then the wave is good, as said, to be a transverse wave. Now let's talk about the next one. His name is the longitudinal wave. Longitudinal wave, in the other way around, is okay. Example of transverse wave: you have the water wave, plucked string of a guitar or a rope. Those are examples of transverse wave. But in a longitudinal wave, example of longitudinal wave is sound wave. Longitudinal wave are waves that exist in region of what we call compression and rarefaction. Compression and rarefaction. In the sense that, if for example, let's consider sound first of all. For sound, you observe that when you talk in air, you talk, you say, you speak, you say something, you observe that that sound travels. As it travels, this is how it moves with respect to the material medium where it's traveling through. What's that material medium? The material medium is air molecules. Now, if it travels, it will get to a point where it will compress the air molecules. For longitudinal wave, the existing region of compression and rarefaction. So as that sound comes out of your mouth, you observe something that first it will compress the air close, but later it will begin to release the air. And at a certain point again, it will begin to close the air down. It will begin to close the air. It will close it down. It will close it down. At a certain point, it will release the air again. To release the air, to release the air, and later he sweeps the air back again. So you observe that this region where it's tight, this region is called region of compression. refraction. But why this region where it's free is called region of rarefaction. So it's a region of compression and a region of rarefaction. Region of compression and a region of rarefaction. So this is a region of compression, a compression and a compression. But these free regions are regions of rarefaction. So when what comes out of your mouth, it compresses the air first. Later it releases. It compresses, it releases, it compresses, it releases. So from there, those compressed is compression, region, and rarefaction. So this system, this is longitudinal wave. The difference now is that the direction of vibration direction of the wave is the same thing as direction of wave. So for longitudinal wave, the direction of the vibration of the medium particle is equal to the direction of the wave. So they move in the same direction. But unlike longitudinal, it is perpendicular. I believe you understand that. Now, this is it. From there, we are now going to represent a longitudinal wave and a transverse wave together. And we can represent the two of them using a common graph. We assume that this region of compression and rarefaction, we assume them to be region of crest and trough. So ladies and gentlemen, let's continue with this. So representation, if you want to represent them, you have a region, and you have something of this nature. You have, this is a vibration. This is the vibration. As the rate of vibration. So as it vibrates, it moves. You see, it will move. For transverse, it will go. It comes, it goes. It comes, it goes. So this region of the highest level, this region is called the crest. Crest. This region of the lowest level is called the trough. So the level of highest displacement is called crest. Lowest is called trough. So for longitudinal wave, we'll consider that this area of high level of compression is crest, and this area of low level, which is area of region of rarefaction, is considered to be trough. So they can also be plotted on the same graph as a transverse wave, represented together. So this is the region of crest and this is the region of trough. So most times I'll represent here as crest, and that is C. I'll represent here as trough, and which is represented as small letter t. So here is small letter t and here is C. So the difference now is that the region from here to here is a wavelength. It's a wavelength. That is a lambda. It's called a lambda. A wavelength is a lambda. So if I write 2 wavelength, it's called 2 lambda. If I write 4/3, this is 4/3 lambda. So, and a lambda is a wavelength. So from this to this point is a lambda, and from here to here is also a lambda, and it's called the wavelength of a wave. The wavelength of a wave. So this distance between 2 successive crests is a wavelength. The distance between 2 successive troughs is also a wavelength. So always remember the graph for representing, and this place here is the displacement y, and this place is x, depends on your notation. So the x axis and the y axis on the graph notation. But always remember, this level of y is what we call the amplitude of the wave, because the amplitude is the highest level of vibration, the highest level of displacement a wave can reach. Now, we have this. So from here, we can pull on to the next level. Let's talk about different wavefronts. Let's see wavefronts. Now, if I drop something, like this, something like a stone inside water, the kind of wave it will give to me, it will be something like this. This way to give to me. So you observe that this thing here is the source of vibration, because this is the thing causing the vibration, that thing I drop inside the water. But the direction, this arrow shows direction of wave. So this direction, this particular direction, this gives me a circular wavefront. So this kind of wavefront is called circular wavefront. So anytime you want to create a circular wavefront, what you need to do is to put a body that is a circular body, throw it inside water. You create something which is circular, or you create a circular wavefront. But in a case where I put something like this inside, and throw it inside water, what I will get is something like this. So this is the source. This is source of vibration. That's the source of the vibration. So this direction, these are direction of wave. This can also be direction of the wave. So these arrows are the direction of wave. So this kind of wavefront is a rectangular wavefront. I can call it a rectangular wavefront. So I can have a rectangular. So if you want to produce a rectangular wavefront, you put a rectangular substance inside a repo tank or a water bath. It will create a rectangular wavefront. So this is what we call wavefront. So wavefront, the kind of wavefront you obtain is determined by the kind of disturbance you put inside that water or a repo tank. So that is wavefront. Now, we have that. We're now going to move on to something else. We want to see terms. There are different terms we use to describe wave. But before then, somebody may ask, what is wave motion? It's simple for you to define. What is wave motion? You tell somebody that the wave motion itself is all about the step by step. Okay, then explain wave motion from here. So from here, you can have, these are wavefronts, rectangular wavefront, circular wavefront. Now, from here you can deduce the motion itself. What is that? The wave motion is the kind of to and fro motion exhibited by waves when they travel from one place to another. So it's a to and fro motion. So when I ask, define or what is wave motion, I tell you that wave motion is the kind of to and fro motion exhibited by waves when they travel from one place to another. So that is wave motion itself. But a circular wave front is obtained using the circular object. Why a circular object? That's circular wavefront. Why a rectangular wavefront is obtained using a rectangular object in a ripple tank. Now, that is that. Let's now consider something else. We want to talk about terms used to describe wave motion. Let's see those terms. For example, when you talk about humans, for example, how do you describe somebody when you see that person? You look at the person and say, he has a long neck. He has a long neck, probably like that of a giraffe. That's description. Oh, that animal has 3 fingers. Oh, that human has 5 fingers. That's description. He has 2 legs. He can fly. It's description. So what are those things we use to describe motion itself? The first thing we'll consider is what we call amplitude. Let's talk about something called amplitude. You see this amplitude of wave? We have amplitude of wave. Describe this first. The amplitude of wave is called the highest level of vibration or displacement a wave can reach. It's always denoted as A, capital letter A. And let's take note of that. So amplitude of wave. For example, do you know that if you get close to the beach side, if you are looking at the ocean, you discover that if you go to different beach, if you get to some beach, you see the wave that is coming. You see the wave moving. It moves. But there are some beach you go to, some of the waves that are coming from those beach is a little bit higher when it's moving. The force, the height of the wave amplitude is higher than some other beach. Depends on that. So because of that, there are some beach that you go to, you observe that when those beach are being allocated for use, for private use or public use, you discover that the people who owns the management of the beach, what they do is that if you observe that the wave coming from the beach is not strong, and you know the fun behind going to the beach is for that wave to be high, that wave to come. When you see the wave, it's fun. It's fun when it comes to the side view of it. So what they do is that they try to bank some part of the water. They put stones to bank some part of the water where the wave is coming from. Heavy stones. I think the dredgers, they do that. They put it by the side so that when that wave is coming little by little, by the time it gets to that banked, slim banked area of it, what will happen is that it will gather. So when it's getting close to you, it packs itself. It got a higher momentum and tends to increase. So you catch that form with it. So it is being banked. And that is what we popularly call in wave principle. It's called, we call it diffraction of wave. What they just do there is diffraction. So they bank it on both sides. So what it is that this slim lining, maybe the water wave is coming from a very high level like this. So they put the stones here. They put stones here. They put stones here. They put stones here. So when it's coming like this, low, when it enters here, it becomes higher here. It becomes higher here, and it becomes higher here. So you by the side of the beach, when the water comes to you, you see it as if it's higher and stronger. So they are banked with stones. That's diffraction. Now, at this point, you observe that amplitude. So if a wave is coming, there are some waves that can reach this level and some at this level. So the one that is higher has a higher amplitude of wave, because that thing you're seeing is a wave. It's a disturbance which transfers energy from one point to another without causing a permanent displacement of the medium particle itself. So from here, that is what we call amplitude. It's the highest displacement and is always measured in meters. It's measured in meters. Take note of that. So the second thing that you can use to describe wave is something we call period of wave. Period of wave. Period of wave is always denoted as T. You see this period of wave and measured in seconds. So this period of wave is different. The difference in that period of wave is time, but it is the time to complete one complete cycle or one complete revolution. So the time to complete one cycle, a cycle is a revolution. You are coming, a wave is moving like this, it turns, that's half. So when you move again, that's one complete revolution. So half, assuming a draw and a crest together, that will complete one. So when you look at it in that form, one complete revolution, for it to one complete revolution, half, one complete revolution, that is what we call the period T of measure in seconds. So the number of seconds it takes for one complete revolution to happen is what we call period. It's measured in seconds and represented in T. The other thing we want to talk about is the guy they call frequency. Frequency is denoted as F and measured in hertz. So most times Hz is measured in hertz, hertz, depending on the English pronunciation of that. Now, hertz. Now this is it. Frequency and F and measured in hertz. Now, you observe that the number of cycles completed in 1 second is called frequency. The number, period was the time taken to complete 1 cycle. But frequency is the numbers of cycles you complete. The number of cycles you have completed in 1 second. So because of that, you will now say that period T is equals to 1 over frequency F. So there's a formula that relates them. T is 1 over F, or F is 1 over T. So please take note of this. This is measured in seconds and this is measured in hertz. So the relationship between period and frequency is that T is equals to 1 over F, or F is 1 over T. So the time to complete 1 revolution is T, and the number of revolutions completed in 1 second is frequency. Now, there's something else that we can talk about to describe wave. Another one is the thing we always call it velocity. Velocity of wave. Velocity of wave. Now this velocity of wave, what is it all about? Velocity of wave. Velocity of wave itself, which is V, is just distance or displacement over time, which is x over t. So that is velocity of wave. But as wave itself come to be, the wave equation cannot be stated as follow. The wave equation states that velocity is equals to frequency times wavelength. Now, that wavelength is the distance between successive crest and successive troughs, which we have explained before. So the distance between successive crest and successive two cross together, that's a wavelength. Two troughs together is a wavelength, which is how I discussed that initially. So velocity is equal to f lambda, where lambda stands for wavelength. So this equation is one of the most important equations, if not the most important equation in the theory of wave. So always remember that V is equal to f lambda. V stands for velocity, f stands for frequency, and the lambda sign stands for wavelength. Good. Now, I can expand this theorem, this formula, by saying that since there is a relationship that states that f is equals to 1 over t, so I can put this f here to represent 1 over t. So therefore, V can also be equals to lambda over t. This is very possible. So you can also say that V is f lambda and that V is lambda over t. So you can use any of them. So these are the equations of, the joint equation of a wave.